Hi, I'm the Lockpicking Cuber, and in this video I am going to be solving the Safecracker 50 puzzle. I got this from not on the high street in the UK, but you can get it from all sorts of other online stores as well. Wow, it's kind of an amazing looking puzzle with a whole bunch of rings with different numbers on. I'm going to have to figure out what those are all about. And it comes with a solution, which I shall put aside and not look at. Over there. It says, Safecracker 50 puzzle, arrange the dials such that all columns add to 50. Okay, and apparently there's a Safecracker 40 puzzle, which according to the website I got this from is 16 times easier than this one. I don't know what that means, how you measure difficulty like that. So I gather that the rings of wood are made of alder. They look like they're kind of different woods, but maybe they're all older and dyed different colors. And the goal is to have all the columns add up to 50. Okay, so I guess this is a column, so there are 2, 3, 4, 5, 6, 7, 8 columns, and they all have to add up to 50. Oh no, wait, I see, there are 16 columns. Maybe that's why it's 16 times harder. That seems unlikely. Okay, so there are 16 columns. We have to make them all add up to 50. Okay, I see. And so some of the numbers, you can have half of any of the given numbers shown at a time. You have to choose which half you want to show, and also how they relate to each other. Whew. Wow, this seems really difficult. Just from the outset and knowing exactly what you have to do, this seems like a very difficult puzzle to me. Let me see, what can I work out? Well, 27, that's really interesting because that's a huge number. And the thing about that is that all the other numbers in its column have to come to 23. And that's 1, 2, 3, 4 numbers adding up to 23. So for example, here we're already at 27 just with those two. That would take it way over. But not only do we have this 27, we also have this 7. So that's already 34. So in fact, we can only have 16 among these 3 digits. Let's just see, if we cover up the 27, we don't get an equivalently high number in the same orbit. Interesting. So I'd like to be able to use this 27 to constrain what comes in this column, but on the other hand, the 27 might just not be necessary. It might not be part of the puzzle. You might cover it up and it's gone. But we do have this 24. Okay, so the total number of all the numbers across all the dials is going to be 800. 16 times 50, 800, right. Okay, I don't quite know why, but I want to work this out. I feel like it's going to be helpful to know the totals on these, and then the totals of every other digit, of every number within the next ring, and then these every others, and so on for all the rings. Okay. So I'm going to start from the inside and work out. So this is going to be 1, 2, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, there are 9 sort of logical rings. Let's call them that. So, and in some cases, every other ring, I think, is going to just have one set of numbers, and then every other ring is going to have 2 sets of numbers, right? So we're going to draw this out in a table. Okay, so ring 1 is relatively easy. So this is 32, wait, is that a 6 or a 9? That must be a 6. Yeah, because they all point in towards the center like gravity. So 32, 38, 44, 61, 69, 88. That one does not have a B. Right. Now, is there some way to differentiate? Okay, so what we're going to do is the A ring is going to be the one you get when you, I'll just pick arbitrarily, so when you line up the notches, the sticking out pieces. I don't know what to call them. So this is the example here. So we're going 14, 31, 36, 54, 71, 91, 105, 110. Okay, so now we switch this around and we get 21, 27, 35, 39, 43, 47. Wow, big difference. I think this is going to be the way to figure this out. So basically you've got the big values and then the smaller values. I wonder if it'll be like that with each ring. Well, let's find out. So now we're going to look at ring 3, starting with 11, 14, 83, 98, 114, 118, and 125. And of course it would have to be the biggest one. It's got more numbers than any of the others. 125, okay. So now we know that that 125 has to be part of the total solution. And the total is going to be 800. That's what we're going to be filling the entire disk with. So as an example, let's say we just worked our way down this A ring here. Let's see what we would get to. So 198, 275, 383, 449, 519, 587, 691, 691, and then 816. Wow, 816. So actually, let's just see what's the highest we could possibly get. I think this is right. So the highest we could possibly get is if we take this one. So 841 is the absolute maximum you can get. Now let's see what the minimum you can get is. So I'm going to put a star into the box. No, I'll put a little dash for minimum. So that's the minimum on that one. That's the minimum. $612, $737. So I think the total's got to be somewhere in that range, 737 to 841. Okay, right, but how many ways are there to combine these sets of numbers together to get 500? That's question one. We've got to, I think this is one way to think about it anyway. Oh yeah, okay, this is the way I'm going to solve it actually. I'm going to say, for each of these rings, so this is, again, this is not about picking columns, it's just about picking the positions of these rings relative to each other. A sort of parity of the ring positions. So it doesn't matter if this is 16 is lined up with that 8, or that 3, or that 11, or that 12, or that 8. Those are all the same from this point of view for now. So I'm just determining which set of numbers to cover up on the dials that have numbers that can be covered up. The question is, how do we make 800 out of these, and are there multiple ways to do it, I suppose? Well, one thing we know is if we used all the minimums, we wouldn't get anywhere near close enough. We'd get 737 and we need 800. So this makes me think you probably can't use this 47. You probably have to have the 110. Yeah, I mean, that's clearly true. Right, because if we take the absolute maximum and we substitute the 47 in for the 110, we're going to go way below 800, sorry, from this one. We're going to go way below 800, right? Because this is more than 41, less than that. So that cannot be correct. You have to, for ring 2, you have to have it displaying 110, which means this one. Yeah, so this ring has to be on this parity where its lugs are lined up with these ones. Okay, so that's that one. This one, much less clear. You could pick either of these and still get to the total. 25 difference here, just 6 difference here. So the other ones where there's a choice, these 3, we don't know. Okay, so we're going to add up all the ones where you have no choice, basically. So this one, this one, this one, I put rings around those numbers here. So dun, 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 and this one. So that's 88, 198, 275, 341, 409, 534. So 534, and then that means from these remaining three, we have to get to 266. So we just have to make 266 out of these three sets of pairs. So there's not very many combinations here, are there? Okay, so ring 4 we have to choose between 108 and 98, ring 6 70 and 95, and ring 8 104 and 98, and the ones we choose have to add up to 266. So, oh, I can see it already. It's those three, right? Let me just check that. So that comes to 196, 266, yeah, okay, so 98, 70 and 98. So the correct answers then are, we cross out that one, we cross out that one, and it was 98 again, so we cross out that. So we don't use the 27. Yay, so the 27 has been eliminated. This is no more. So this ring is going to belong here, or here, or, you know, it's going to be, wait, yeah, so there or there, basically. One of the ones that covers up the 27. The row, so that's row 8, ring 8. Ring 7, we have no choice. That's this one. Ring 6 is this one, and there we want the A one, which is this one, I think. Let's just check. 8, 21, 41, 61, 69, 70. Yep, that's the one for this one. Ring 5, we have no choice. Ring 4, it's the B one, so this one's to be off like that. The remainder is always position A, so lined up. Okay, so something like this, for example. 17, yeah, we're not there yet. Right, so that exercise is complete, but does it help me? I'm not entirely sure that it does, actually, but I have some information. I no longer have to choose the values that I'm using, I just now have to choose how I line the values up with each other. Okay, well, let's see if, sticking with these values, I can make a 50 somewhere, just at random. Let's pick a column with this 0. Let's pick this 0 column here, and let's see if I can make a 50. So we have to use the 13 and the 0. There's no choice about that now. There used to be a choice, right? If I was including the 27, I could have had any of these numbers, but now I can't. So this has to be 0 and 13. Right, so what's the highest combination of those we can get to? This one is 33. Wow, that's huge. 21. That's also 33 up there. Wow, so we've got two different 33s, both 15 and 18, and they are opposite each other. That is very interesting. Is that just a coincidence? I wonder. They are by far the biggest pairings of this type where they're both fixed. So I'm not counting these type, but this type. So 33, that means the remaining numbers can only add up to 17. So we clearly can't use a 16 unless we had a 1 and a 0. Oh, actually we could get to a 1 and a 0, right? So we could go, I want to turn everything all at once. We could do that, 1, and then where would we get a 0 from? I don't know, maybe we can't. We can only get the numbers that are displayed currently, right? We can't get at any other numbers, basically. So 33, 34, 48, and then that would require us to have a 2 here. We don't have a 2. The smallest number we can get at here is 6. So 33, 41, it requires me to find a 9 in here and a pair of zeros there. We do not have pairs of zeros available. Can't be that either. What about this one? 6 and 16. So now we have to have a 1 and a 0. Oh, wait, I'm an idiot. There. There. This is it. Okay, so this is how we get to our 9, right? So we've got 15, 33, 34, 41, 49. Wait, what? 16, 17, 50, right. 16, 17, 50, okay. 13, 24, no, but the others aren't right. So this is one way to get 50 in both of these columns, but it has not worked on the other columns, sadly. Okay, so what we're thinking is we've got 15 and 18, that's 33, and we think this has to be 8 and 8, so that's 41. So we need to make 9 out of these two values in here. Right, and it has to be these two brown ones, not these lighter coloured ones. So it could be that 8 and 1, for example. Let's see what that does for us. Yeah, so this is an example where we have 15, 18, 1, 8, 8, 17, yeah, which comes to the right total. The numbers around it don't come to the right total. You can see that's 32. So if we assume that these are the right values for these two columns, then actually each of these three numbers has two positions it can be in, because there are two ones opposite each other. So this 1 can be here or here, this 8 can be here or here, and this 8 can be here or here. So we can think of that as 3 binary values. We're going to consider this current position to be 0, 0, 0. And what we're going to do is we're going to look and see, say, taking this column here, can we get this to work by putting some combination of these two light colours in there? So what we'd need are these to come to 12, 32. So we'd need 18 from these two values here, which at a quick glance we can see you can't get to. So that's fine. So that just means 0, 0, 0 doesn't work. And I think we can say, if we call this one 0, 0, 1, where we just rotate that all the way around, we can see it's not going to make any difference because it doesn't affect any of the values in this column. This is still wrong. So 0, 0, 1 is also wrong. So we'll put that back to 0. So now we're back on 0, 0, 0. We want to do 0, 1, 0, which means rotating this way, like so. And now what we have in this column is 12, 29. So this time we want to get 21 in here, which we can get with this 8 and 13. So let's just try that out. Right, so that works here. So we've got 12. Yeah, so this one works. What about this? 24. No, this is now wrong. Right, 15, 23. Yeah, 39. So this is no good. So we're going to say that one's wrong. And we're going to try 0, 1, 1. Although actually, yeah, we can try 0, 1, 1. See if that does any good, but it doesn't fix this one. So that's also no good. Okay. So now we want to try 1, 0, 0. So we turn this one all the way back. I'm just being super careful about this now. And now this one needs to go all the way back. So now we're on 0, 0, 0. And then we want 1, 0, 0, which means this big one down here going all the way around. Try and do that without affecting anything else. Yeah, there we go. So that's there. Right, so if we take this column, okay, this column, 20, 36, this column's now correct, actually. I think this is it. This is it. Oh, wow, that took me way too long, but I think I'm there. So let's just check every column. We're going to start with this 8, 13, 23, 6. So that looks right. 29. Yep, that's correct. So now this one, 13, 37, 50, yep, 33, 34, 42, 50. 15, 26, 45, 50, 33, 44, 50, 26, 36, 50. Haha, that's it, it's solved. They all add up to 50. That was very fun and enjoyable. So the trick to it was realizing, well, first of all, that there was a fixed required position for the rings in terms of sort of parity with each other. So that was step one, which took a little while. And then step two was realizing that this required there to be these 15 and 18 across each other. So that was easy to notice. That means 33. And that means basically having to have 8 and 8 across from each other. There was no alternative to that. So once you got to that position, that meant that you had to put this 1 and 8 in here and here. So you basically were forced to have this column have these values. And that just left, in theory, that left 64 things to try. But actually you only needed to try 4 of the 8 combinations of these 3, because turning this didn't make any difference to every other one. And you could just look at the other numbers rather than needing to try them all. You could just sort of add them up in your head without turning them. So there we go. I don't know how long that took me. It was maybe a couple of hours. Very satisfying, very enjoyable. I'm guessing if I were to try and solve it again, it would still take me a little while, like 20 minutes or something like that, if I could remember exactly what I did. But maybe if I try it again in a year, it'll take me another couple of hours. That would be my guess. So there we go, a really nice fun puzzle. Safecracker 50. There's a Safecracker 40. I don't know if it's exactly the same principle or not. I haven't seen anything about it, but it might be worth trying out. So there we go, all done. I hope you've enjoyed watching this video. If you have and you'd like to see more like it, please hit the subscribe button. Thank you so much for watching this one, and I'll see you on the next video. Bye.